Yeah, okay. So welcome back, and our next speaker is Balázs Bárány from Budapest, and he's talking us about dynamical covering sets on self-similar sets. So please.
Yes, thank you very much, and also thank you for the opportunity to give this talk here. And this is absolutely unrelated to the fact that what I would like to talk about is a joint work of two of the main organizers of this seminar. So I would like to talk about the dynamical covering sets of self-similar sets. And so what is the main setup for us? So just like before, we have a iterated function system of similarities in Rd, and I will denote by lambda I the contracting ratios for these maps. And yeah, it's well known. There is this non-empty compact set, which is called the self-similar set, which is invariant with respect to this IFS in this sense. And also there is a unique probability vector, which is Borel probability vector, which is invariant with respect to this IFS in that sense. And our standing assumption will be now that we have the open set condition. So we suppose that there is this open and bounded subset, which is invariant, namely all the maps of the IFS is mapping it into itself, and the images via two different maps are disjoint. It's also a well-known theorem by Hutchinson that in this case, this set is very, very friendly and nice. Namely, it's S0 alpha regular. So in particular, it has positive and finite S0 dimensional Hausdorff measure, where this S0 is nothing else than the similarity dimension here. And also, Cayley and Moldin showed that the Hausdorff dimension of the measure, so it's, like Feng and Hu, that it's exact dimensional. And in this case, it was much earlier, and it's nothing else but the entropy over the Lyapunov exponent ratio. And if you have such kind of self-similar set, then there is a natural dynamic in the background. Namely, you can define naturally an expanding dynamical system on the self-similar set as follows. So if you have a point which comes from this set, FIU intersected with lambda, then apply on X the inverse of this Fi, and if it comes from the, namely, if it comes from the, so it belongs only one of these Fi of lambda sets, then apply the inverse of Fi. Otherwise, apply whatever you like to apply that function. But it doesn't matter, because, for example, even with respect to this measure, the boundary cases when there are multiple options to choose this function, we'll have zero measures, so they are negligible with respect to these dynamics. So what we are particularly interested in this talk will be the dynamical subsets of these self-similar sets. And what do I mean by dynamical subsets? Still some more setup. So these self-similar sets behave very well with the symbolic space. So we have n-many functions, which means that our symbolic space will be the infinite sequences formed by these n-many symbols corresponding to these functions. And let sigma be the usual left shift operator. And we can define this natural projection pi from the symbolic space to the attractor in the usual manner. And what is the good part is that this natural projection conjugates these dynamics, what we have seen before, with the shift dynamics in this sense. Okay, and just to be able to speak about stuff, let me introduce some further notation. For example, by sigma star, I will denote the set of finite sequences, and by this I absolute value for finite sequence, I will denote the length of it. by I restricted to n, I will denote the first n symbol of I, so the restriction of it to the first n symbol. Also for finite words, the cylinders, just to save some space. If you have a finite word, then let lambda I be the corresponding product, and also pi the corresponding product of the probabilities and the contracting ratios from before. And if you define a Bernoulli measure on this symbolic space, which means that nu p is a Bernoulli measure corresponding to this probability vector, if you choose the measure of the cylinders as pi, this basically means that you choose the symbols independently and identically at each position in your infinite sequence. According to this pi, so the position k, you choose the symbol I with probability pi, and everybody is independent. Every position is independent, and you do at every position the same thing. But what is nice, that if you push forward this measure, nu p, this Bernoulli measure, with respect to the natural projection, then you get back your self-similar measure, what we have seen previously. And now, with this setup, we are asking properties of dynamically defined subsets. And first of all, what are dynamically defined subsets? So one type of such kind of sets is the so-called shrinking target set. So take a rate, and just for fun, let this rate, which is a sequence converging to 0, and fix a point x. This will be your center of the shrinking, and this will be your size of the target. And you are searching for those points from the attractor whose orbit along this natural dynamics on the symbol, on the self-similar set, will hit the small rn shrinking neighborhood of x infinitely often. And this guy can be represented as a limb subset of the inverse images of these balls, these target balls. Other type of such kind of thing is the recurrent set. Here also have some rate, some shrinking rate, but here you are interested in those points who are returning on it into its own neighborhood, into its own shrinking neighborhood infinitely often. And the third class I would like to talk about is the dynamical covering sets, whose are the points who, so you again pick a point x and some rate shrinking down to 0, and you will be interested in for the covering set for those points who will be covered infinitely many times by the orbit, so by the orbit of t of this fixed point x. So this fixed point x wanders around the self-similar set, its ball is shrinking always, but you are interested in those points who will be eventually covered infinitely many times. Okay, and these are coming very naturally from more general dynamical systems, but I'm only talking about now the self-similar situation. And you can also add for these systems a little spice, because you can also say that this is a very, very geometric object, and you can replace the geometric approach with a symbolic approach. Namely, instead of the radii of balls, you can choose a function from integers to integers, which will be the length of the cylinders, and you assume that it goes to infinity, so you take longer and longer cylinders. And what you are doing is basically consider this shrinking target set on the symbolic space. So you're interested in those infinite sequences whose orbit along this shift dynamic will hit this cylinder set, this longer and longer, so it's smaller, smaller essentially, cylinder set infinitely often, and you push it forward to the self-similar set. And you do the same association with the recurrent set, and you also do the same association with the covering set. So instead of looking at geometric rates, we have now symbolic rates, which means the length of the cylinders. And what you want is to cover these points infinitely often and with the cylinders along the orbit of some fixed point. Okay, so these are the two different approaches. In the case of shrinking targets, these two approaches are not really different. So the shrinking target set, in many aspects, in many ways, has been studied very widely, and I have to apologize in advance if I missed someone from the list of people, but this is a really, really wide list. So if you think that I should have mentioned someone, please feel free to interrupt me and tell that I omitted this and that, or me, and then it was very, very nasty of me. But what I want to say is, is a result of Hill and Bárány. So whatever results of other people I will state are usually holds in a much higher generality in other contexts. What I state is the particular version of the result for exactly or self-similar open set condition setup. Okay. So what Hill and Bárány showed that if you calculate the shrinking rate, what is the shrinking rate in the geometric approach? Well, what is the exponential shrinking rate of Rn? So what is the exponent? This means more or less that Rn goes down to 0 by e to the power minus alpha n. And in the symbolic approach, you are looking at that how fast, what is the exponential rate of the diameter of the images of these cylinders. What is the diameter? You take the contracting ratio and multiply the contracting ratios according to this cylinder set. So what are these values? And the Hausdorff dimension of both shrinking target sets will be the unique solution of this equation. So in shrinking target case, there is no big difference with these guys. In the case of recurrent sets, there is. So Surrey and Wang showed in that case that if you are considering this geometric aspect of recurrent sets, then it basically behaves like shrinking targets. So you calculate your exponential shrinking rate of your Rn radii, and then the Hausdorff dimension of the recurrent set will be the unique solution of this equation. But if you change to the symbolic approach, then I'm pretty sure that it's done by someone, but I couldn't find any better reference than or special case of the joint work with Sasha. Namely, we need also to assume that the length of the cylinders, you're interested in what is the linear growth. So ln goes like n times beta, and you also need to assume that it's strictly smaller than 1. Then this Hausdorff dimension of this symbolic recurrence set will be the unique solution of this equation. You see that there is some clear difference between these two guys. And also these recurrent sets in many aspects are studied by many people. And what about the dynamical covering set? It's also widely studied. In the covering set aspect, maybe I should have also wrote here the first place Dvoretsky, by choosing the center of the balls as identically distributed and independent random variables. So if you draw this is also a very widely studied aspect, but what we are interested in when the centers of these balls are dynamically driven. And for that, Liao and Surrey showed the following. Actually, Liao and Surrey did not show that. Liao and Surrey showed for expanding maps on the line, but everything goes through word by word. So you have this Rn shrinking rate, and what you assume is that it's monotone decreasing. So these are the radii of balls. And what you are asking is that what is the polynomial shrinking rate of Rn? So Rn in this case shrinks like n to the power minus 1 over alpha. And depending on alpha, you get this weird result. Namely, if you choose your center point, here this x, who is wandering around, according to the measure mu p, and for almost every x, you see that the Hausdorff dimension is this random covering set is alpha until alpha reaches the Hausdorff dimension of this mu p measure. Then it will be the multifractal spectrum of the local dimension of this measure mu p until this quantity, whatever this quantity is at the moment. But after that, it reaches the top, and then the dimension will be maximum. And so this multifractal spectrum of this local dimension is basically nothing else than the Fourier transform, no, that's not a Fourier, Legendre transform of the LQ spectrum of this mu p measure, actually the nu p measure, but it's the same because of the OS. Furthermore, they also showed that for almost every point, if your alpha is strictly greater than this quantity, then you almost surely cover almost every point with respect to the S0 dimensional Hausdorff measure. And if it's strictly greater than that quantity, then you almost surely cover really every point infinitely often. Okay, but this is a weird big formula. It's much more informative to look at this. So what is this orange dashed guy? This orange dashed guy is the multifractal spectrum of my self-similar measure. This is the smallest possible value. This is the largest possible value. You begin to increase the value alpha. 1 over alpha is the graph. Then you grow linearly along the identity, the y equals to x, until you reach the tangent, right? Because the multifractal spectrum is uniquely tangential to the y equals to x function exactly at the Hausdorff dimension. And after that, you grow along that until you reach the peak, until you reach the top. And this is the value which corresponds to the local dimension, which corresponds to the dimension maximizing measure. And after that, you reach the full dimension. And until your multifractal spectrum runs out, after that, you really cover everything. This basically corresponds to the result that they also calculated the Hausdorff dimension of the complement. Namely, of course, until the peak, until the maximum, your Hausdorff dimension of the complement must be the maximal. But after that, the complement follows the decaying part of the multifractal spectrum until it runs out. And after that, it will be an empty set because you cover everything. So this is the behavior, what we would like to understand when we use the symbolic approach. And this is our result. So let Ln be a monotone increasing function, which will be the length of the cylinders. It will go infinite, and it will go logarithmically. And Ln will grow like 1 over alpha times log n. Okay, so we are looking at the symbolic dynamical covering set and push forward to it. And you can compactify this formula much better, because the Hausdorff dimension of this set for nu p almost every center point is the infimum of this function p alpha q, where you take the infimum only for q between 0 and 1. And this p alpha q is the unique solution of that equation. So it seems like some natural generalization of whatever the shrinking target dimension and whatever the LQ spectrum is. This has also some nice phase transition. Namely, you will follow the value p alpha 1 for alpha values who are smaller than some certain alpha naught value. And this alpha naught value is the unique solution of that equation. Of course, for first, why on earth does this equation has a unique solution at all? And why does it have a solution? Yes, believe me, it has a unique solution. After that, it follows the infimum. So after that, for alpha values between alpha naught and this other value, again, somehow corresponding to the dimension maximizing measure, you follow the infimum. So this infimum over the 0, 1 corresponds to the infimum of the whole real line. But after that, if you reach this value and you continue your journey for larger alphas, then your dimension will be S naught, because if you substitute here q equals to 0, then you get S naught. And you also get the same type of results for the measure. Namely, if your alpha is strictly greater than this value, then you almost surely cover almost every point with respect to the S naught dimensional Hausdorff measure. And if your alpha is greater than this maximum, which is basically minus the logarithm of the smallest probability, then you almost surely really cover everything. Okay, big formula, let's see a picture. So what are the components? This is the P alpha 1. So this is the solution of this equation for P alpha when Q equals to 1. Seemingly this is a line. No, it's a strictly convex map if you have here, in a typical scenario, it's very rarely a line. Then you see here this Legendre transform-like thingy, so the infimum for every q of this function P alpha q, it goes from this minus log P, actually this should be P max, and that should be P min, sorry for that. And this is something a little bit more curvy, but looks like some multifractal spectrum thing. It has one unique maximum, and which really reaches the Hausdorff dimension of your set. And what does the covering set follow? So until this value alpha naught, you are strictly convex. Then you are tangential, so this red line and this orange line are tangential at alpha naught. Then your dimension becomes concave until you reach the top. Then you becomes full Hausdorff measure. Your spectrum runs out from below you, and then you really cover everything. And we have the same analogous result for the complement. But there, for the complement, you need to take the infimum for the negative case. And again, there was the phase transition. If your alpha value is strictly smaller than this alpha 1, this peak value, then this infimum is S naught. Otherwise, your infimum over the negative guys is the infimum over the Vorion line. And the same for the measure theoretic guys. So you follow the maximum until you reach alpha 1, then you follow the spectrum part, and then your set runs out. This guy, of course, is not necessarily goes down to 0. It can stop somewhere here about some positive value. Okay, so this is the main result. I would like to tell you 2 examples, actually 3. One is that if you choose your probabilities according to the dimension maximizing measure, then this is the measure where you reaches the stage that you cover almost everything, almost surely the fastest, which I mean that you need the smallest alpha 1 value. Right, so very quickly go up and very quickly go down. So this means that for every other value, this peak point is somewhere further. But there is another important guy. If you choose the uniform measure, then actually this is the point where you reach, with the smallest alpha, the I cover everything almost surely case. Right? This is when you need the smallest alpha to cover that. And in this case, for the uniform case, all these alpha values where you observe phase transition are collapsing into one point, and you here follow P alpha 1 until the maximum, and after that you really covered everything. There is no in between, no further phase transitions there. And there is one other particular case, lambda, when you choose the contracting ratios to be homogeneous. And in that case, this P alpha Q can be written by the LQ spectrum. And basically, this infimum, what we have seen before, becomes really the Legendre transform of the LQ spectrum. And we get back the special case of Liao and Surrey in that case. Okay, and So these are the important examples. And I would like to say a few words about the proof. Nothing technical, just the idea that by this P alpha Q, what we have seen here is the answer, because, okay, it looks nice, compact, tidy, but why on earth is this the answer? And the answer is the following. Let's consider two more natural pressures. So we have this rate, who is the length of the cylinders, and let us define M of n as follows. M of n is the number that for how many positions will you get n length cylinders. Basically, you take the inverse of n. This will be a long time when, let's say, L, P1, LP2, and so on, or taking values. And this is a long, long period when you are covering with n length cylinders. Okay, you sum up with respect to these n length cylinders. And what is this probability here? This probability here is exactly the probability that in this time, in this mn very, very long time, it's so long that I have to move backward. So in this long, long time, okay, it's not exactly that, but more or less, you pick this I cylinder, you cover at any time. And what is this lambda I to the power s? If I want to cover the covered n-length cylinders, this will be the weight of this n-length cylinder in the covering argument for the Hausdorff measure. And what is this other guy? This other guy is the same, just this is more or less the probability that the I cylinder don't appear. And this is good for covering the complement. And what happens is that this infimum between 0 and 1 is the unique root of this pressure, this probabilistic pressure P1. And for the infimum with negative Qs is the unique root of this P2 pressure. And this is some, massaging formulas and sums. But from this, it's clear that these guys can be used to provide for the covering set and the uncovered set some actual cover to determine the Hausdorff dimension, and with some Borel-Cantelli arguments, you can get the almost sure upper bound. For the lower bound, what we have is a kind of variational principle, I think, for this generalized P alpha Q pressure. Namely, if you take the infimum for positive Qs, then it will be the supremo of the entropy over Lyapunov exponent of every Bernoulli measure with probabilities Q for which this quantity is smaller than alpha. And the symmetric case happens for negative Qs. And this variational principle is very, very useful, because then you can provide lower bound for the complement set. This is why it's maximal and then follows the pressure. And also for the covering set for sufficiently large alphas who are larger than this alpha naught. So you can use this variational principle. And basically for the lower bound, for the covering set, if alpha is smaller than this alpha naught, so when you follow the P alpha 1 value, we actually forced to construct some kind of random mass distribution, which pushes the dimension up, because in the result, and many results from these dynamical covering theorems are using the mass transference principle. But there is one problem in this symbolic aspect with the mass transference principle, especially when the contracting ratios are inhomogeneous, that it's insufficient. If you apply the mass transference principle, your scaled balls or scaled cylinders, actually balls, will not large enough to reach the mass and actually be able to transfer it down and provide you sharp lower bounds. So that's why we are forced to construct it. And one final word, I'm pretty much interested in what is going on at these phase transition points, like here. So really, not only tell me that if I choose L, the growth rate to be strictly greater than this, then I cover everything. Really tell me, what are the functions? What are I give you an IFS, I give you a probability vector, I give you this monotone increasing function. This thing here must be a 0, 1, a tail event. So this means that I have to be able to tell that for these maps, exactly what is the minute when you cover everything or you don't cover everything. So can you give me an actual Dvoretzky type result for that case? And thank you very much for your patience, because really this is all what I wanted to tell you. So thank you for your attention.